Hey everyone, and welcome to NoelsMarine. Today, we're going to go deep, right down into focus on the understanding RT-Flex marine engines and critical speed operations. We've got a great agenda today. We're going to cover the marine engine problem, enter the RT-Flex engine, how electronic control works, the smart engine advantages, understanding critical speed, and finally, the barred speed range. We'll learn what an RT-Flex engine actually is, why it was developed, exactly how it works, and its main features. Plus, we'll dive into this really important concept called critical speed and how it affects both conventional cam engines and camless RT-Flex engines. So let's just jump right in. Section 1, the marine engine problem. To really get why engineers developed the RT-Flex engine, we first have to understand the limitations of traditional marine engines. You see, in traditional engines, fuel injection timing was fixed mechanically. This led to some pretty big issues, like poor combustion during low engine loads, higher fuel consumption, increased smoke emissions, and constant wear and tear on the camshaft components. So to overcome all of this, the RT-Flex engine was born. And there were three main reasons for this shift. First up, fuel efficiency. Think about it. Ships consume absolutely massive quantities of fuel every single day. Even a tiny reduction in fuel consumption can save huge operating costs. The RT-Flex improves combustion and optimizes fuel injection, which brings fuel consumption right down. The second reason, emission reduction. Modern ships have to follow strict environmental regulations, and the RT-Flex really helps cut down on nitrogen oxide emissions, smoke formation, and those unburned fuel particles. Finally, the third reason was for better low-speed operation. Conventional engines usually struggle at low RPMs, but RT-Flex engines, they can run super smoothly, even at very low speeds. Section 2. Enter the RT-Flex engine. So what exactly is it? Well, an RT-Flex engine is an electronically controlled, low-speed, two-stroke marine diesel engine. It's mainly used in large merchant ships. We're talking container ships, bulk carriers, massive tankers, and other large cargo vessels. And it's worth noting, the RT-Flex engine was developed by Wärtsilä Sulzer.
Now here's where it gets interesting. Unlike those conventional marine engines we just talked about, the RT-Flex engine doesn't use a mechanical camshaft for fuel injection and exhaust valve timing. Instead, it uses three key things. First, an electronic control system called WEX. That's the electronic brain replacing the camshaft. Second, it uses a common rail fuel injection system. And third, a hydraulic servo oil system.
Section 3. How electronic control works. Let's break down this working principle, step by step. Okay, step 1 is crank angle detection. Basically, a crank angle sensor detects the exact position of the piston. It then sends this signal straight to the engine's computer, which, as we mentioned, is called WEX. That stands for Wärtsilä Engine Control System, and it literally acts as the brain of the engine. Then we move to step 2, computer decision-making. The WEX's system takes that info and calculates the engine speed, the engine load, the exact fuel quantity required, the fuel injection timing, and the exhaust valve timing. It's incredibly smart. The system constantly adjusts the operation to guarantee maximum efficiency. Step 3 is getting that high-pressure fuel ready. Fuel is continuously available in the common rail system, and the pressure is intense. We're talking approximately 100 megapascals, or about 1,000 bar. This fuel can be heavy fuel oil or marine diesel oil. If it's heavy fuel oil, the temperature is generally maintained around 135 to 145 degrees Celsius just to keep the proper viscosity. Next up is step 4, fuel injection. The WECS system sends an electronic signal causing the injector to open hydraulically. Because of this, fuel enters the combustion chamber at the absolute perfect timing and quantity. The result? Better atomization, better combustion, less smoke, and greatly improved engine efficiency. And finally, step 5, exhaust valve operation. Remember, there's no camshaft operating the exhaust valve mechanically here. Instead, hydraulic servo oil steps in to do the job. The servo oil pressure sits at around 200 bar, which provides highly accurate exhaust valve timing and much better scavenging efficiency. Section 4, the smart engine advantages. Now, back in conventional marine engines, the camshaft mechanically controls fuel injection timing, exhaust valve timing, and starting air timing. The big disadvantage there is that the timing is fixed. Your flexibility is literally zero. But in RT-Flex engines, electronic control handles all of these operations. That means the timing actually changes based on the engine load, the operating conditions, and power requirements. Because of this flexibility, combustion improves, fuel efficiency increases, and emissions drop. An easy way to remember this? Just think of a conventional engine as a manual system with fixed timing, whereas the RT-Flex is like a highly responsive, smart automatic system with flexible electronic timing. Let's quickly recap its 5 main features. First is the common rail fuel system, keeping fuel at about 1,000 bar pressure, so all cylinders get fed from one high-pressure rail. Second is electronic fuel injection, where the computer completely controls the injection timing, quantity, and pattern, like pilot, main, and post injection. Third, you've got hydraulic exhaust valve actuation, using hydraulic oil for precise timing. Fourth is that flexible low-speed operation we talked about, allowing smooth running at very low RPMs. And fifth, the total elimination of the conventional timing camshaft, which massively cuts down on wear and tear. In actual ship operations, these features are a real game changer. Fuel consumption drops, meaning ships save huge amounts of money on long voyages. Maneuverability during berthing and unberthing gets so much better. Smoke emissions plummet, engine reliability goes way up, and maintenance costs just drop. Section 5. Understanding critical speed. Now, let's pivot and talk about a totally different but absolutely crucial concept: critical speed. So what exactly is critical speed? Well, to put it simply, it's the dangerous engine RPM where excessive vibration occurs due to resonance. This dangerous vibration happens when the natural frequency of the shaft system perfectly matches the excitation frequency produced by the engine's firing forces. In plain English, the shaft vibrates way too much at a specific RPM, and this specific condition is what we call resonance. It's kind of like pushing someone on a swing. If your push timing exactly matches the swing's natural movement, that swing is going to go higher and higher, right? It's the exact same concept here. Engine firing pulses can match the shaft's vibration frequency, and when they do, torsional vibration increases significantly. Running continuously at this critical speed is incredibly dangerous for the engine. It can lead to severe crankshaft damage, cracks in the intermediate shaft, damaged couplings, excessive bearing wear, an intense noise increase, and just overall severe vibration. In worst-case scenarios, the entire shaft could fail. Because of this, continuous running at critical speed literally must be avoided at all costs. Section 6. The barred speed range. To help prevent these disasters, engine manufacturers define a restricted RPM zone known as the barred speed range. They usually make this range slightly wider than the exact theoretical critical speed, just to give operators a safe buffer. For example, this restricted zone might be between 48 and 52 RPM. Ships must never operate continuously within this range. Instead, the engine needs to pass through these RPMs very quickly. Accelerating quickly through this zone helps prevent that dangerous resonance and protects the shaft from damage. Now, you might be wondering, does critical speed even exist in these advanced camless RT-Flex engines? The answer is yes, absolutely. Critical speed exists in both conventional camshaft engines and camless RT-Flex engines. Why? Because critical speed depends mainly on physical factors, things like the shaft's natural frequency, shaft stiffness, mass distribution, engine firing order, and propeller interaction. It doesn't actually matter if the engine has a camshaft or not. Now, it is true that RT-Flex engines control combustion more smoothly because of their flexible fuel injection timing, better cylinder balancing, and smoother torque distribution. That means the vibration effects can be reduced, but critical speed cannot be completely eliminated. That barred speed range must always be respected. So remember this key takeaway. Even though RT-Flex engines provide much smoother combustion, they can't eliminate critical speed because it's a fundamental physical characteristic of the shaft system and resonance. So let's wrap this all up. The RT-Flex is a highly advanced, smart, electronically controlled marine engine. It swaps out the conventional camshaft timing for a common rail fuel injection and hydraulic control system. This gives you better fuel efficiency, lower emissions, incredibly smooth low-speed operation, and reduced maintenance. But at the same time, as a marine engineer, you absolutely must understand critical speed to avoid catastrophic shaft vibration. Grasping how RT-Flex engines operate and managing these critical speeds is vital for your oral examinations and for practical, everyday onboard troubleshooting. If you found this breakdown useful, give the explainer a like, share it with your fellow engineers and maritime cadets, and subscribe to NoelsMarine for more detailed deep dives, understanding RT-Flex marine engines and critical speed operations. Hit the bell icon so you never miss an upload, and we'll see you in the next one.